Hello and welcome back to Dubeke Consult. Today we'll get to see how you can apply wind load on your structure while designing with Prota. If you're designing with BS Code, you should understand that getting to 10 meters and above, you are mandated to apply the effect of wind load, or your building should be designed to resist the effect of wind speed when it is being applied on your structure. Once you get to 10 meters and above on a flat terrain, there is a clause there that says on a flat terrain. And why is it on the flat terrain? Because you can have something like this, your location of design. Let's say you can have something that looks like this, and something, and you can have your structure here, and this can be a flat surface, and you can also have your structure here, maybe also about the height of 6 meters thereabouts. Maybe there's a retaining wall here, but you can have this different scenario. This can be your location of proposed building, and this can also be the location of the proposed building. So in these different cases, there are ways which you can estimate the effect of this wind load, because it is ideal, it is clear that the wind that will be acting on this structure, let's call this structure A, and this is B. So the effect of wind that will be applied on this structure at this level will be different from the effects of the wind that will be applied on this other structure, all right, just because of this topographical factor. So it mandates that you apply your buildings are designed to resist the effect of wind load at 10 meters and above on a flat surface. So let's see how we can apply our wind load on this very structure that we're working on for some time. So to apply your wind load, what you need to do is come to analysis and come to building analysis. Then you come to wind and story loads. All right, you click on expand all stories. So as you can see, we have, this is our wind on direction X and is 0. Also our wind on the direction Y is 0. All right, so these are our notional loads, because these are the horizontal loads. These are our notional load that was applied in the previous video. You can go back to our previous lecture pre-analysis to see how we are able to apply these notional loads. So the notional loads has been applied the respective X direction and Y direction, while our wind load on direction X and direction Y is 0. So we can estimate this load manually, or we can as well use the wind load calculator that comes with Prota structure. Alright, so for this class we'll be calculating with this wind load calculator that comes with Prota. So you click on this, and before you estimate this wind load, what I will advise you do is you come back to, you go from here, cancel, and come back to loading combinations and click on this loading generator. All right, so on this loading generator, come back to horizontal loads and ensure your wind loading is ticked so the effects can be applied. So click here, add this, click OK, and click OK. All right, so now you can come back to applying your wind load. So we'll come to wind and story settings. We'll come to wind and story settings, and we expand this, is still 0, and we come to the wind load calculator. The most important factor while you are estimating your wind load, or what you need to know about your building while you are designing it to resist the effect of wind load, is you have to get familiar with your location. That is the location of your proposed structure, and you also have to get familiar with the code of design. So for this case, we are designing with BS code, and the respective code is BS6399-2 that we'll be making reference to. You can as well change to any of these which you are comfortable with or which you can design with, but for this class we are designing with BS6399-2. So the most important thing is your location of proposed structure, because it's that location that will determine your basic wind speed, the height of the buildings that are close to your proposed structure, the level above the normal sea level, and other parameters that can be used to estimate this wind load. And to make this more realistic, we will be choosing a specific location for this very building to make this more realistic. So in a real life scenario, you can understand how you can estimate or get all these values. We are actually in the technology age, so most of these values you can get them online if properly tutored. So we'll be estimating, or sorry, we'll be picking a location for this very structure, and we'll be picking a location somewhere in Lagos, Nigeria, and we'll be picking a location somewhere in Lagos, Nigeria, so we can get all these parameters at ease. All right. So firstly, we will launch our Google Earth, and let's pick any random location in Lagos. Let's pick a random location, and we'll work together and see how you can estimate this in a real life scenario. All right. So we'll go to, let's say, Lagos, and this is Lagos as you have it. Now let's come back to our Prota structure. Now the first factor here is your basic wind speed, and your basic wind speed is measured in meter per second. So you can get this from your ISO map, you can get it from your local authority if they have an updated wind map, but you should be very careful. Now while you're making use of that ISO map, you should investigate the design code it was estimated to. Now what I mean is, if it was estimated to the BS code or with the procedures of BS6399, then the basic mean speed value was calculated as an hour interval, right? It's calculated per hour. Why, if you are designing to Eurocode, or if the map was estimated to Eurocode, then the average mean speed is taken as 10 minutes interval. So if you have a map and it is designed to your BS code, there is a rate of conversion for you to convert from your BS code before you can apply it to your Eurocode. So you can't use the same value that was discovered with a map designed to the BS code and use it for your Eurocode. So make an investigation of your area and understand the code of design that very map was predefined to. All right, so this helps you a lot, so you don't overestimate or underestimate. Okay, so let me just bring out the BS6399. So this is actually BS6399, and this is the UK map. So you will all have the basic wind speed of each areas. All right, so you can see this. If you are designing for a structure around this area, you have 31. Around this area, you have 30. So this is exactly what your ISO map looks like. So you can get the location. Let's say we are designing for somewhere around Liverpool. You see the basic wind speed here is 23, while somewhere around this part of Preston, you know, the basic wind speed here is 24. Okay, and in some cases you can be designing to a older code. Maybe the map you are making use of is a much older code. All right, so the code I have, or the code I have in my location right now, or with me I have access to, was designed to an older code, which is CP3 chapter 5 part 2. Okay, so if you observe the basic wind speed of the BS code is given at an hourly mean value. So this was calculated, or the map you should be using to design to BS code should be calculated at an hourly mean value, and it differs from the CP3 part 5, which I said I am making use of, which is based on a 3 seconds gust value. So you see, this other code was estimated at 3 seconds, while the other code was designed per hour, and Eurocode was designed every 10 minutes. So there is a way you can convert. However, the hourly mean basic wind speed is subsequently converted into a gust wind speed for use in design by the gust. So you can go through this code and see the method in which you can convert these values. All right, so that's the most important thing about your basic wind speed. Understand you get the value, you get the map, then understand the code it was designed to, so you don't end up overestimating or underestimating. All right. So the next thing here is your, so we'll put all these values and we'll see how you can calculate all these values and get this and get them for your design. So the next thing is your minimum wind pressure. All right. So this is a very important factor that is also affected by each and every other of these very parameters here. So your minimum wind pressure, right? Because Prota structure, uh, it designs its wind load as an area load. All right, it applies it to the floor level as an area load. And when we are talking about the area load, we are talking about the length of a building. The length we multiplied by the height, then the effect, which is this pressure, for us to get that area load. Let's say we've assumed this and this, and to see how important this value is, then I will come back to our y direction. You can see the pressures here. We've also come back to our x direction. Then you will also come back to our y direction. You will also see the value of those pressures here. So this is the minimum assumed. This is like the minimum assumed. And one thing you should understand is, as you move higher, the code, due to its calculation, it will keep increasing these pressures. But you can also calculate this manually for taking procedures that are in your BS6399. All right. So this is the value that is used to multiply your area for you to get this load. So let's come to our this part and let's get the area load of this part. So if we multiply, because it's making use of this one is making use of the longer side. So if we multiply the length, this is the length, and our height is 3 meters. We said it's an area load. Okay, so length times breadth. All right. So 3 meters. So 3 meters multiplied by, this is the width, so with 31.58. all right. So these three values are the same because they are also making use of 0.65 as the minimum pressure. So let's try this one that has 0.83 or 0.98. So if we multiply this by 0.83, so we'll have something close to this. All right. Keep in mind that this is an approximated value. So if you use the real value, you will have something close to this. So this is an approximated value. All right. So this is how the load that are applied on each stories are calculated. So you need to be careful of the pressures, the minimum pressures that you are applying to each stories, because it's from there that Prota will estimate further values going forward after you leave your first, second, and third story. Most times, or let's try this second value as well. Let's try 3 meters, which is the height of the story, multiplied by the length, because you are applying on both x and y direction. So we are calculating for the y direction now. So if we take 3 and multiply by 31.58, right, and we'll multiply this by, let's use 0.98, which is this other value, which is this one. So you see we have something close to this. All right, so this is how your loads are being estimated. So let's come back to our parameters, and now we know the importance of this minimum wind pressure. So we can't just estimate any value of our choice. All right, so we'll keep this. I said we'll come back to estimating each of these values, but both of these are greatly affected by every other of these parameters over here, and this has to do with your location, as we said. So let's come back to our map and see how we can get all these values. You can actually get most of these values from your map, and some of them from your GPS, some of them from even your camera. We are actually as the technology age, so things are quite easier. All right, so let's come back to our map, and we said we'll be designing somewhere in Lagos, Nigeria, and let's pick a specific location. You can try Eco. Okay, don't think there will be free land there. Let's come to okay, let's try Victoria Island, Lagos. Okay, All right. So we'll look for a free plot. We'll look for a free plot over here if we can find, and we use that free plot as our sample, and we can see how we can estimate each and every of those other parameters. So I think I can see some free plots here, and I would like to design this structure at an area that already has existing building. As you can see, this place, no, this is a free plot, but it has literally no structures surrounding it. Because if we come here, if we come back to our Prota structure, like I said, we have an option here for town and country. So when you're speaking about town, you're talking about areas that are developed, that has buildings surrounding it. If you have something like this, if you have something, or let me go back to Prota, I think there's an example there. Okay, so you have something like this. Let's say this is your proposed structure, right? This is your proposed structure. So you should understand that if there are buildings close by, when the wind comes, when the pressure, the magnitude of that wind, when it comes, it will touch some of the structures surrounding it before it even gets to this one. All right, so that is what defines your town, right? Not basically because it is in Lagos or it is in a local part of your country. So what defines your town or your country is if it has buildings surrounding it that can resist the effect of the wind speed, before the wind load, before it gets to your proposed building, or it is an open area. All right, it can be a newly sanfilled area, which just like this part that does not have building close to it, and the wind that is coming with come directly on your structure. So I want us to design at a town area. So let's look for a location. Okay, I think there is a free space here. All right, I don't know this place, but I think there's a free plot here. So let's assume this to be our location of design. All right, so let's say we have our structures covering this area. So how can we get these values? The first value here is our H0, and our H0 is the average level of rooftops of the building, or height of permanent obstruction upwind of the site. So the average height of buildings that are in that very surrounding that will resist or will reduce the effects of that wind when it's coming to your proposed structure. So to get this, we can use we can search this very street. Let's see the street here. We have Sinari and we have Munis. Okay, so let's use let's drag this man over here and let's see if we can have a street view. Okay, let's have a street view here to see the surrounding buildings and if we can estimate their height. Okay, so you can see this is the location, this is the location, this is around the location. So we can get the height of, we can get our H0 just mere looking at this map. This so I believe this should be our proposed location. Okay, this should be our proposed location. So we can get the average height of our buildings and surroundings just from our Google Earth. So if you look at this, we have, this is a story 1, 2, 3, 4. So this is approximately, this is 5 stories. All right, and judging by the average of 3 meters per floor, 5 stories, this is around 15, which is almost same with our proposed building, or same with our proposed building. This should be more than 5. We should have 1 here, judging by the height of this fence, 1, and we should have the second story 3, 4, 5. So this is average of, and we should have 1 here. This should be around 3 stories. All right, so let's exit this view, or let's minimize this and come back to our Prota structure. So our average height is between 3 stories to 5 stories. So for that case, let's use an average of 12 meters height for 12 stories. For 4 stories. Let's assume by that location and by what we've seen so far, we are confident that if we use a minimum of 12 this we do. If we use a minimum of 12 meters, this we do. That is 4 stories, 3 multiplied by 4. All right. So we'll assume a height of 12 meters. Okay. And the next thing we'll do is we'll come back to our wind map to assume this to get this other value. So let's come back to our Google Earth and we'll exit this. Okay. Then we'll zoom out of our location. And if this structure will cover, let's say, this perimeter, what is the distance from its location to the surrounding buildings that will be obstructing this wind speed that is coming? Okay, so we can easily measure that from this Google Earth. Okay, so let's come here and use our, there's a ruler tool here. You can see there's a ruler here. So we'll come here and let's see the unit of measurement. This is in meters. Our x0 is in meters as well. So we'll come and ensure this unit is in meters. So if our building is stopping here, somewhere here, let's say it will cover this perimeter. All right, and it will cover somewhere like here. So let's estimate this value. We can measure from here to the surrounding buildings, and this is around let's say 40 meters. This is around 50 meters. Okay, so around 50 meters, and also coming to this direction, we have around 60 meters to these surrounding buildings. Okay, then the next one is the building will also stop somewhere here. So let's also measure from somewhere like here to this part, and average of about 30 meters. Okay, also from here to here, average about, so we'll take an average of 50 meters. All right, so we know if you are taking 5 meters, we are wrong. If you know we are taking 10 meters, we are wrong. If you are taking about 40 to 50 meters, no, we are actually on the same alignment. So we'll take the maximum value, which is around 50 meters. Okay, we'll take the maximum values around 50 meters. So we'll type this to be 50 and unit is in meters. And the next thing is your altitude. Okay, so this is your delta S, your altitude, and your altitude as defined by your BS code. Okay, if you have something like this, as said earlier, you can have something like this. Okay, then going up, you can have something like this. So your altitude is your height above the, let's say this is your normal sea level, your datum, your normal sea level. So this is the height above your normal sea level. All right, and if you are designing for a structure here, it is the altitude over here. And if you're also designing for this structure, you will not take this altitude, you will take the one that is here. Okay, let's say they are together, or let's say you can physically see these changes. Okay, so you have to take the altitude that is here and not this very one. And sometimes you might not see these changes. Okay, sometimes you might not see these changes with your bare eye. It can be distributed over a long distance. Let's say it can be distributed just slowly over a very long distance. Let's say from Lagos to somewhere like Port Harcourt. You know, there will be a change in terrain that you can't see with your bare eyes. Okay, so each of those cities, each of those locations, they have the altitude, and you can get this from your GPS. You can get this from your GPS. Let's come to, so you can get this from your GPS. All right, so if you look at this GPS, if you look at this, you will see the GPS will give you your coordinates, and as well it will give you your height above the normal sea level. Okay, it will give you your height above the normal sea level. You can get this online as well, or you can also, there are some cameras, there are some apps you can use, and when you get to that location, you just have to launch the app and it will give you the height above the normal sea level. So let's work with this very first picture. So if you look at this very first picture and the location, this was during an investigation on this very site location. So if you look at the altitude, this is 102.6 meters above the normal sea level, and this is somewhere around Lagos. This is somewhere around Lagos. And if you come to a different location, let's say you are going to somewhere like Kaduna, all right, if you are designing for somewhere like Kaduna, you can see the altitude here. It's very high. This is about 600 and let's say 650 meters above the normal sea level, because like I said, this value can be distributed over a long distance and you will not be able to, identify the change in altitude with your eyes. Okay, so let's see how this affects our values. If you come to Prota structure and taking an example of these two pictures, the first one is about 650 meters above the normal sea level, while this one is about 102 meters. Okay, so if we come here, we'll come back to this part and we'll take our altitude as 102 meters. Okay, then let's come and check the result for our values. You see, this is our pressure is still at 0.65 on x direction, and on y direction we still have, there is a change in value here, but it's not much. I think it has moved from 83 to 96 because of that increment in altitude. Okay, then let's come back to our parameters and let's take this to the location in Kaduna. If we take this to about 650, all right, and we'll come back to our WX, so you can see we don't have same value from story 1 to the final story. This has already been altered by the code because each of those locations, they have their height above the normal sea level. All right, and what you should know about this wind is when it's acting on your structure, let's say we have locations like this. So this part can be a hilly part, this part can be shallow, so this height will determine if the wind is coming, the effect that is coming on it, the magnitude that is coming on that very building, that proposed building. So we come back to our Prota and you can see the difference. So each of these values, they are very, very important. So like I said, you can get this value from your GPS. You can also get it from some applications like your timestamp camera, and this is technology age. You can get most of these things online. Okay, so that's it for the altitude. You should get the location of your height above you should get the location of your proposed building and be able to get the real and the ideal height above the normal sea level. So the next thing we'll be looking at is the distance to sea upwind. All right, so this is another very important factor. You should understand that if we have something like this, okay, and we'll have another location like this, or let me go with this other two. And these are different locations, and let's say you have your sea, your water body, the sea over here, right? You have your sea over here. You will observe with me that if you have this at one location in somewhere in Lagos, when you get to visit this location, the magnitude of wind you experience around this sea is always different from, let's say you go to your beach area. All right, you go to your beach area, or you are designing for a building that will be a beach house. So the magnitude of wind speed that will be applied on this very building due to the effect of this wind here will be different from what you have over here. All right, this part will experience more and a higher magnitude of your wind. Okay, so this is another factor that also affects the magnitude of wind speed that is being applied on what our structure. So you should get this location, and you can and get this distance to your C. So let's come back to our Prota structure and get this distance to the C upwind, and let's come to our Google Earth. So the unit of measurement is also in meters, and let's look for where we can see a water body over here. So I think there's a water body here, there's water here, but I'll prefer to go with this bigger one, this C, and or this one, okay? Because why I'm choosing to go with this one is from my observation, this part they are all some field area. I think this should be the Eco-Atlantic city axis. So if I'm designing for a realistic scenario, I feel they might some fill this area as well. Maybe it's a work in progress. So I would like to go with something around this part that we can see is a free water body or the Atlantic Ocean itself. So the minimum distance is what we'll be using. We were using the minimum distance for this very scenario. So we can measure from here, and let's see we have a distance of about this is about 1,154 meters, which is about 1 kilometers. Or let's see how far we can go. Let's see this part. This is about 1.3, and let's see. So the minimum is about 1 kilometer, which is this. Okay, if you are going with this part, you will see that it's very close to this C, so the effect will be higher. Okay, the effect will be higher. So what I will do is okay, I will go with this water body. I will go this very water body. Okay, so this is about 550 meters, or let's say about the minimum, so the effect is considered. Let's go with 450 meters. Okay, so we'll go with 450 meters from this very location of design to our water body, okay, our C. So we'll escape, we'll come back to our Prota and come back to our Prota structure, and we'll take this part to 5. Let's take 450. Okay, the distance to C upwind. All right, so with this you've been able to estimate each and every of this value. And I said we are designing for a town area. Okay, do not forget we are designing for a town, because we are designing for this area that is characterized by other existing structures which are almost the same height of our proposed structure. So it's actually defined as a town area if you go through the parameters of BS6399 part 2. While if you are designing to somewhere over here, maybe this is a new estate or a new field area that doesn't have obstruction, then you are designing for country area. Okay, so let's come back to Prota, and for this Lagos location, my location, I'll be using a height of 150 meters above the normal sea level. Okay, so the next thing, the last parameters we'll be estimating here before we come back to this is our structural properties, which is our dynamic factor. Okay, so our dynamic factor, it speaks about the particular type of structure that you are designing to. If this video has been helpful to you at any point, do not forget to like and subscribe to our channel. Do not forget to like the video, subscribe to our channel, and follow us so you get updated anytime we post more videos in this series. Okay, so you need to get a proper understanding of the building you are designing for. So this is our welded steel frame. If you are designing for, because this design can be for a warehouse, so you have to use a different scenario. But in this case, we are designing for a building that has structural walls, which is our shear walls, our lift, and stairs. All right, so this is an example of the structure we are designing for. You can have this other building. This is something like an open area. Okay, more like an open area that has just the stairs and that has just the stairs and probably the shear walls. But this one, we have the shear walls, we have the stairs, we have other adjoining walls that can actually contribute to the rigidity of our structures. Okay, so we will going ensure that you choose the appropriate dynamic factor here. Ensure you choose the appropriate dynamic factor. So I'll click on this and click OK. So like I said, my code was designed to, my ISO map was estimated to CP3 part 5, which estimates its value at every 3 seconds gauge speed. Okay, and converting it to the BS code, I was able to, and the value for my location of design is actually 34, but 36 is used in design. And when I converted this, I was getting something between, because of the height of my structure, something between 28 and 30. So I'll be going with a wind value of what, 30, and my minimum wind pressure, I will take this to 0.7. Okay, let my minimum be 0.7 due to my calculations and my estimations. All right, and the primary wind angle, I will leave this at 0. This is in cases where, let's say, you have something like this. You have something like this. All right, and you want to apply to your wind speed, you want the effect to be calculated at some specific angles. All right, so you should know that if this is our 0, then at this position we are talking about 45 degrees. All right, then this angle should be 45 degrees. So this other angle, because what it does is it applies on both the x and the y direction. Okay, that's what it does, both this direction and this direction, as an area load. So the area will be calculated and the pressure will be applied on that area. All right, pressure is calculated and applied on this area. So if you're applying to this direction, it means the opposite side, it will also come at this angle, and subsequently at this angle, and what, because the effect will be replicated at this angle and also at this other angle. All right, so let's come back. If you take this to 45 degrees, you observe this, please. Let's take it to 45 degrees and you will see this will turn to 135. The next one will turn to 135, which is 45 plus 90. Okay, so let's take this back to 0, and we've decided our height to be 12 meters at an average. Our x0, which is the distance from our proposed location of our proposed building to adjoining buildings that has the capacity of resisting some effects of this wind speed. So we have this at 50 meters, and our altitude is 150 meters above the normal sea level, and the distance to our upsail to the sea upwind is 450 meters, as gotten from what, our Google Earth. We are designing for a town location. We are just ensuring we do some checks, and for this case, a framed building designing to BS6399. And let's come to see the results. So this is the result. This is the load that will be applied on this level. While considering all these parameters, these are the loads that will be applied on each respective levels. All right, calculating as an area load. So we can click to generate our report. Okay, so we can save as a PDF, and so these are our values and these are our resultants. Okay, these are the applied wind load on both x and y directions. So now that we've successfully estimated these values, we can apply them on our stories now. Okay, so you can see it has been applied to our story. So on our direction x, here we have our wind load applied. The magnitude of our wind load now converted from meter per second with calculations has been applied as 40.8 kilonewton. Okay, that's on the x direction, and on the y direction we have a value of 66.3 kilonewton. This is on the corresponding y direction. So there will be subsequent classes to see how you can estimate these values yourself, because there are some versions of softwares and there are some other softwares that does not give you this advantage. So you can actually estimate these values yourself using procedures in the BS6399, and you can use it for other softwares, let's say like Start Pro. You know, there are other softwares that you have to do some a lot of manual calculations yourself. So you can apply to those other softwares, and these are the values we have for each of the stories. Let's expand this, or we can drag this down. So this is the value that will be applied at, this is the load that will be applied at this story. Keep in mind that BS6399 mandates you designing your structures to resist the effect of wind load. And to get these parameters, you should never be shy of asking your clients of this location, because imagine this is not designed to resist this magnitude of load. Okay, you should not be shy of asking for the information of the proposed location of your structure so you can get these values yourself. All right, so always ensure you get all this information and estimate in the proper way. So with this, we can click OK. Then our wind and story loads has been applied to our structures. All right, so the next step after this is to run our analysis. So if this video has been helpful to you, please do not forget to like, subscribe, and turn on the notification bell so you get notified anytime we post new videos in this series.